Now, what is a train of impulses? We'll discuss the mathematical analysis of this whole process. As of now, it is nothing but continuous impulses occurring after every specific amount of time. So if you see the first impulse, or I would say there is one impulse at t equal to 0. The second impulse is at t equal to ts, then 2ts, then there is an impulse at t equal to 3ts. This is on the positive side. On the negative side, we have impulse at minus ts, minus 2ts, and you can see I've put the dots here. That means there are infinite such impulses. So the time gap between any two impulses turns out to be ts, and hence ts will be the time gap between any two samples that we are going to read, and hence ts is called sampling period. For example, if ts is 1 microsecond, that means after I read the first sample at t0, the next value of x of t that I will read will be at t0 plus 1 microsecond. The third value I will be reading will be at t1 plus 6 microsecond or t0 plus 12 microseconds. The third value I'll be reading will be at t1 plus 1 microsecond or t0 plus 2 microseconds. So after every 1 microsecond, we will read one value from x of t. So that becomes my sampling time period. Output of ideal sampling process will look something like this. If you observe in the sampling signal, which is nothing but signal number 2, all the impulses are of constant height, which simply means that the area under every impulse is a constant value. For simplicity, I'll take this to be 1. So these are all unit impulse functions that we have taken. But if you observe output of the ideal sampling process, which is signal number 3, has the same train of impulses, but every impulse has different height. Different height will indicate different area under every impulse. Please remember that all the impulses always have infinite magnitude. So when I'm showing impulses of different heights, doesn't mean that different impulses have different amplitudes, because amplitude or the magnitude of every impulse is always infinite. Then what does the difference in heights represent? It simply represents the different area under the impulse. If it is unit impulse function or unit impulse in simple words, the area under that impulse is 1. But after you multiply unit impulse function with some constant scaling factor, let's say if the impulse is multiplied by number 2, that means the area of that impulse becomes 2 and not its amplitude. So you can see the third signal represents nothing but the sampled version of x of t. You can see all the impulses will represent the different values that we have read from x of t, and these impulses will also occur at the same time instance 0, ts, 2ts, 3ts, etc. on the positive side. On the negative side, minus ts, minus 2ts, and so on. So the gap between the two impulses is ts, and you can see I've also shown the dotted red line. It represents the shape of my original signal x of t. So we have read a lot of values from x of t. The only loss which is taking place is between the two values or the two impulses in this case. If I have chosen ts to be small enough, in that case this loss will not affect anything. We will be able to recover the original signal x of t back. But always remember that we will never get exact version of x of t back, because there is always a small amount of information loss taking place in in any form of sampling process. But as I told you earlier, if ts is small enough, if the gap between two impulses is small enough, the loss of information is less, and we can always obtain approximate version of x of t which will be very much close to x of t, or in other words, the difference between the recovered signal and x of t is something that we cannot easily make out. So this is the description of the signals when they existed in the time domain. So we have taken some signal x of t, we take the sampling signal, which is a train of impulses, and we get the sampled version of the signal x of t. Now, one very important conclusion: how do you obtain sampled version of x of t? all you have to do is multiply the first and the second signal. If you multiply x of t with the sampling signal or the train of impulses, you can see that the signal between the two impulses is 0, so the multiplication will be 0. And when you multiply x of t with the impulses scaling factor will change. They will now become the corresponding values of x of t at those time instants, and that we are representing with different heights of the impulses, and that's how we get the sampled version of signal. So in time domain side, we define a very important relationship, which is that x of t, the sampled version, is multiplication of x of t and s of t. The criteria that we are looking for can only be derived if we find the frequency domain representation of all the three signals.